Good morning, everybody. I want to talk to you today about just some of the things we've been working on in the last couple of years. And a lot of the work that I'm going to present today is actually not my work, but it's the work of Jonathan Hodges and Jason Floyd. Jonathan is actually here today, so you can direct a lot of the questions to him. I'm going to give a very basic, broad overview of these developments. There's a paper that comes with this talk, and also there's, of course, the FDS manuals that have, the details. But I just want to get across the basic idea here in my presentation. So it's always been a problem when you're modeling fire that you have to include, realistic objects burning in realistic spaces. And unfortunately, in our labs, most of the time, we burn things underneath a large hood in which we collect the exhaust products and measure heat release rates and the yields of smoke and CO and various other things. And of course, at the end of these experiments, you get a curve like the one that's shown in the upper right-hand corner here. That's the heat release rate of the object burning as a function of time. Now, unfortunately, when you are doing your designs, oftentimes you have to, for various reasons, either directly put this heat release rate curve into your model, which isn't actually necessarily a good idea, because if this couch were burning in an actual house, the burning rate is going to be quite different because the thermal environment around that couch is going to be quite different than in an experimental lab. So then oftentimes the authorities having jurisdiction will force you to use one of these typical T-squared fires. And I got to tell you, I've been in this field for 30 years. I hate these T-squared fires. They've just evolved to the point where we think that every fire behaves like this. It ramps up to a certain heat release rate, holds steady, and then ramps down. And ultimately, we want in our models more realism. And so the approach has been, and this started back in when we first started out. We had this idea that if you know the heat release rate of the object that you can get from something like a cone calorimeter. In other words, you take some small sample of, the seat that you're sitting on, and you put it in this small apparatus, you expose it to a certain heat flux, and then you get the heat release rate per unit area directly from this bench scale apparatus. You then can put that into the model, and you say when that object reaches that ignition temperature, and so you have to set some sort of ignition temperature, then the burning is going to follow what you measured in the cone calorimeter. Now the problem with that, though, is that when you use the cone calorimeter, you have to specify a certain exposure heat flux, and typically that's 25, 50, and 75. And oftentimes when you have cone measurements done on a material, you do it at those three heat fluxes, and you get a curve that looks like what you see in the lower left. Shown in green, red, and blue would be the heat release rate of some material at 75 kilowatts per meter squared, 50, and then 25. Obviously, the less exposure you have on the material, the slower it's going to burn, the longer it's going to last. So it should have dawned on me 20 years ago, but I'm thick, that, hey, instead of just putting in one curve, why don't we put in 3 curves, and based on what the model is predicting the heat flux to be, extrapolate or interpolate between these 3 curves. And that's exactly what Jason and Jonathan have done. Here's a really simplified, version of what I just said. There's a couple of different things. One is you want to scale your burning rate based on the exposure. Okay, so if you have two sets of cone data, one at 50 and one at 25 kilowatts per meter squared, and they look like what you see here in blue and orange. If you're running this in FDS and your predicted exposure to the material is, say, 35, well, it kind of makes sense to take some sort of linear interpolation between these two curves. And so what Jason and Jonathan have done is they've automated this procedure so that as the heat flux to the surface changes, and literally changes grid or time step by time step, okay, the burning rate will adjust. In the end, you know, mass will be conserved, energy will be conserved, but you'll get a much more realistic burning rate. Another issue they've come across is that when you burn items in a cone calorimeter, you have to choose a particular thickness for that item. You know, if it's a slab of plastic, you know, it's going to be a 1/4 inch, 1/2 inch, whatever. And the thickness of the material is going to affect its burning rate as well. In a very simplistic way, here's two cases. The blue would represent a relatively thin sample, because that thin sample is going to heat up more quickly than the thick sample, even if the exposure is the same, okay? And so they have worked out a way, again, to interpolate between these two curves to give you more realism. So you don't have to take whatever the item is, whatever the material you're interested in, you don't have to take that exactly to the testing lab and burn it at exactly that thickness. You can burn it at whatever thickness has been burned before, and then scale things appropriately when you're running your calculation. So how does this change your model setup? Fortunately, it doesn't change it all that much. This was my marching orders to Jason and Jonathan, like, let's keep what we have, but then just add a few more parameters to enable this scaling to take place. So the way things have worked in FDS for the past 20 years is that one specifies an ignition temperature, which you can get from a cone calorimeter experiment. You specify the sample thickness. You specify a heat release rate ramp that you get from the cone calorimeter, except now instead of just specifying one ramp, you'll specify as many ramps as your cone testing. So if you tested at 25, 50, and 75 kilowatts per meter squared, then you will produce 3 ramps instead of the single ramp. Reference thickness and reference heat flux, so those are the new parameters. So those simply indicate to the model, to FDS, what the cone data was measured at, okay? So if you only have cone data for 50 kilowatts per meter squared, you put that in. If you have it for 50, 25, 75, or any other heat flux, that's an array, and you can dial in the different exposure heat fluxes and the thicknesses of the sample in the actual cone experiment. And there's a final parameter here called inert Q ref, and that indicates whether or not the cone calorimeter experiment was done in air or in nitrogen. And this is particularly important if you're dealing with something like wood or any material that chars, because obviously it's going to behave differently in air and in nitrogen. So that's yet another little adjustment that needs to be made under the hood while the calculation is being run. Now, the way that we checked that this stuff was working well is we did a lot of simple experiments that are now part of the verification cases. I should mention that, a big step forward has been made in the fire research community, where a lot of cone data from the past is starting to make its way online. In particular, FSRI, which is the research institute under Underwriters Laboratories where Jason Floyd works, they have taken it upon themselves to do dozens and dozens of different materials, cone data and other bench scale measurements, and put all that data online. There are also other organizations that have put their cone data online. So we're now starting to see literally hundreds of data sets from the past, with measurements done with a cone calorimeter. But again, in order to use that data, you have to have these scaling rules in FDS, because the cone data that you find online is not always complete. You might have it at one heat flux or one sample thickness. So the machinery that has been built into FDS will adjust for that. And here's how things were done. So you can see here that here's some cone data done at 25, 50, and 75, shown by the solid green, red, and black lines. And so what they'll do is they'll say, okay, suppose I only had the 50 kilowatt per meter squared data. How well can I predict the heat flux? How well can I predict the burning rates at 25 and 75? And that's what you see with the dashed blue and green lines. Okay? Now, of course, it's not perfect. So if you only have data at 50 kilowatts per meter squared, you can extrapolate to 25 and 75. The extrapolation is fairly good, but it's obviously not going to be perfect. And so they played this game with the hundreds of data sets that they had collected. Basically, I'm going to take some cone data, I'm going to extrapolate. If I have cone data at 25, 75, and 50, I'm only going to take one of those data sets, and I'm going to extrapolate to the other two and see how well this method works. And this plot here is showing the measured and the predicted heat release rates that they get from this verification exercise. And you can see that it's quite good. I think where things are a little less accurate is when you're in the the low heat flux regime, which is not surprising, because if any of you have ever run a cone test at like 25 kilowatts per meter squared, a lot of times the burning rate of the material can be less predictable and less repeatable. But we were very pleased by this, that we can take this cone data and use it in our simulations. For some of the full-scale work, we've been involved over the past decade or so in a, how shall I call it, a round robin with other modelers and experimentalists. And the idea is that the experimentalists run a series of kind of simple fire experiments, and then the modelers all take a crack at trying to match the results of those experiments. One of them is known as the SBI, the single burning item test. This is used in Europe quite a bit, where you take whatever, if you're interested in the flammability or combustibility of a wall lining, okay, you take two representative panels of that wall lining, you form a corner, and you put a fire right at the base of those two panels, and you start the fire, and the rate at which the fire spreads will give you some kind of indication of how flammable or combustible that material is. So there were some experiments done just with the plastic PMMA, and we tried to model these experiments in several ways. There's the what we call the S-Pyro method, which is what I've just described, where we take actual cone data for this material and we dial it into FDS and we run the simulation. Then there's the method by which we take kinetic properties of the material. That's a whole other talk, but it's a more detailed way of trying to predict the burning rate. So you use things like thermogravimetric analysis, or TGA, to determine the kinetic parameters of the decomposition of the material. And we can plug that into FDS. And what we found was that using the S-Pyro method, in other words, using the cone data directly, gives you a more robust, repeatable, and reliable simulation, obviously because you've got the results of that cone data directly put into the model, whereas when you're trying to predict things more from first principles, there's just more uncertainty in all those dozens of parameters that you measure that are related to the breakdown of the material itself. So you can see here on the left, these are our predictions done with the detailed kinetics method, and on the right, the results done with the S-Pyro. So if you do have cone data, and again, the databases are starting to grow, this is a method that we would recommend because you're less likely to have those uncertainties introduced by the detailed kinetics. I mean, ultimately, we'd all like to do things from first principles, but from a practical point of view, sometimes using, actual bench scale data of the actual material is going to give you a more accurate representation of the burning of that object in full scale. I'm just going to point out here that this has been used by Jonathan at Jensen Hughes, where they were looking at fires in scale-down rail cars and applying the same principle of taking small samples, running the cone calorimeter on them, and then putting them into FDS. And some of the results you can see here. The results are not perfect by any means, but if you're burning, rail car seats and plastic materials lining the outer walls of a rail car, to get in the ballpark and to have the same sort of basic functional relationship for the burning rate is a big step forward. With my 4 minutes and 36 seconds left, I am going to also touch upon some work that I have done in the last couple of years along with Randy McDermott, and we've been looking at doing three-dimensional heat conduction in solids. And this is something that people have asked us for years, right? Why can't we just do three-dimensional heat transfer in solids like, if I use ANSYS or Abacus, or there are any number of finite element codes out there that do a wonderful job of heat transfer, heat conduction through complicated solids. Well, it's always been the strategy in FDS to use a simple one-dimensional heat conduction calculation normal to the surface, because when we're doing fire simulations, most of the time the solids that make up the boundaries of our computational domain tend to be relatively well insulated. I mean, if you look at this room, for example, right? I mean, the wood, the plaster, whatever else this room is made up of, it's not highly conductive. However, you sometimes get into situations where you're looking at structural steel, or even, compartments made with steel walls, and in such cases, it is important to consider the fact that the heat isn't just being conducted directly into the solid, but rather it's also being conducted laterally. And so here's just a simple, test case that I put together, just showing that, okay, we have a solid plate, we have some other solids coming out of it. This is steel. I'm heating it up in the corner, and I'm watching the heat transfer, through the steel and then ultimately up into the other protrusions, if you will. Now, our first attempt to do this used the simple idea that if you take the gas phase grid and just extend it into the solid, right? Because these solids are really just gas phase grid cells that have been blocked off, and just do the heat transfer calculation in the solid like we do it in the gas, except we only do the diffusion part and not the convection part, okay? So you just have, heat impinging on the surface of the solid, and then cell by cell transfer that heat in all three directions. The problem with that technique, though, is that it is explicit instead of implicit. Explicit meaning that it has to do with the way the time stepping is done, the way that the temperature in any given grid cell is updated from one time step to the next. And when you have an explicit time step, it means you are constrained in how big your time step can be. And we found that the time step to do these kinds of calculations was going to be smaller than the gas phase time step. And we know with LES, the gas phase time step is already pretty small, and to make that time step even smaller for the solid phase calculation would be prohibitively expensive. And in fact, as the grid gets finer and finer and finer, this solid phase time step constraint gets worse and worse and worse. So we had another idea to do this calculation using the same implicit solver that we use for the normal 1D heat transfer, the Crank-Nicholson updating scheme. And the idea is that you do a 1D solve in one direction, and then at the next time step you do it in the other direction, and then in the next time step you do it in the third direction. And in doing so, you're splitting the three-dimensional updating of the internal temperature into 3 time steps, right? So you do it X first, then Y, then Z. The details are in the paper, but I think that kind of gives you an idea of where we're at. And this is just some verification cases. Here you have like an I-beam, you're heating it up on the side. We can compare our simulations with this technique against data that we get from a very finely gridded finite element routine, and we're quite happy that in many cases we can match things well. Here's a more practical example where we have a steel structural member in a compartment. These experiments were done in Sweden at SP probably 10 years ago. And now we can actually look at the beam heating up on one end, and we can consider now that, you know, some of that heat is not only going to penetrate in the perpendicular direction, but it's going to penetrate down the length of the beam. Okay, I'm out of time. Again, this is a very broad overview. The details are, you know, the devil is in the details, and those details are in the paper, but I think that these two features are modest extensions of some of the algorithms that we've been using for the past 20 years, and they give you more flexibility. The only caution is that, especially with the 3D, people think, oh, well, why don't I just turn 3D on everywhere? Well, no, there's a cost to it, and sometimes it's just not appropriate to use a 3-dimensional algorithm instead of the one that we have now, especially if you have, you know, non-conductive surfaces. To do the calculation in 3D is just going to cost you more with very little gain. So we're going to caution people to use these features with the understanding that this isn't like a full-blown, you know, finite element package like ANSYS or Abacus or these various other things, where you can have the most complicated 3-dimensional object and do the heat transfer in all its glory. No, we just are extending a little bit the methodology that we currently have. Okay, thank you. I'll wrap it up there.
Thank you, Kevin. Do we have any questions for Kevin?
They're going to say, I tried this and it didn't work.
Yeah, I've got 6 bugs. Yes. Okay. Well, if there's no questions here and I don't see any online, thank you, Kevin, and
Great.
we'll go to our next speaker.
Okay.
Thank you.